In our previous lectures, we've talked about developing things like the strain displacement relations. We've talked about developing equations of motion. And I want to remind you that even when we talked about the definition of stress, in none of those cases did we talk or specify how the material was characterized, whether it was an elastic material or a plastic material. Those developments were outside of the behavior of the constitutive law. Constitutive law is that law that relates stress to strain. So I'm going to write down just quickly for you some equations that we had already developed. And I'll just say, recall, we had developed, number one, the equations of motion, and also equilibrium, but I'll write them as equations of motion, which looks something like sigma ij, comma j, plus rho bi, plus rho bi is equal to rho ui double dot. Okay, so that equation, or set of equations, represents actually three equations, and it gives us actually 9 unknowns. So the unknowns are 6 stresses and 3 displacements. Okay? We also talked about the strain displacement relations. And this is kind of the expansion of your sort of rudimentary delta L over L to displacement, which looked like epsilon ij is equal to 1/2 ui comma j plus uj comma I. That gives us, remember, epsilon ij is a symmetric tensor, so there's 6 unique strains here. So this gives us actually 6 equations, but it also introduces 6 more unknowns. So 6 more unknowns. There's actually 9 unknowns here. We have strain and the displacement, but it's only 6 new ones in strain. So if I sort of tally this up, so far I have 9 equations, and I have 9 plus 6, 15 unknowns. Okay, I'm just going to remind you that also, recall, the constitutive law was not used for these equations. But you also notice that in order to solve these equations, we need 6 more equations. So to solve for these 15 unknowns, we need 6 more equations. Okay, these 6 equations are going to be supplied by our constitutive law. And remember, a constitutive law just says that sigma ij is related by some function, we'll just, for the moment, just call it f, some function of epsilon ij. So it's a way to relate stress to strain. So we're going to develop the equations in this class, or at least in this section, for a linear elastic material, but I want to back up to just an elastic material to begin with, and just say that we can define elastic material behavior as follows. So we say an elastic material is going to be characterized by, number one, that stress is going to be a unique function of strain. And what does that mean? It means it's a one-to-one mapping. The other feature about an elastic material is that it completely recovers its original shape once you remove the loads or the displacements that you've applied. So it doesn't change its shape permanently. The corollary to all of this are these features. So I'll say a corollary is that the elastic loading response is going to be independent of the load history. So it's sufficient just to say what the strain is, and we'll be able to read what the stress is. It doesn't matter what happened to the strain previously. The other corollary to this is that when we have a load-unload cycle in an elastic material, we don't dissipate any energy. This is actually in contrast to the kind of behavior we're going to talk about in this class. So this class being called Plasticity and Viscoelasticity. Both plasticity and viscoelasticity have the capacity to dissipate energy during the load-unload cycle, and both in the elastic and the viscoelastic case, the loading response is absolutely dependent on the load history. It depends on what has happened previously. We can have basically two types of elastic behavior. So elastic behavior can be either linear or nonlinear. So let's just note that. And furthermore, any material response that's not elastic is called inelastic. A classic example of this would be plasticity. So plasticity is an example of inelastic behavior. Let's go ahead and draw some pictures just to kind of illustrate these examples. So here, let me just say examples. So the first, let's just do typical linear elastic material. So there's a stress strain. It's linear in that. And the load up curve and the unloading curve are the same. So this would be a linear elastic material. Looks like this. Okay. If we were to draw another material, that would be nonlinear elastic, it could have some shape to it like this. The feature that makes it elastic is that it follows the same curve up and down, and so that would be nonlinear elastic. And then finally, we can have inelastic behavior, which would be well described by plasticity. So here's our stress strain curve. And maybe we load up, right? You can't just tell on the loading curve what material behavior is. You have to unload to actually see what happens. But if it unloads, let's say like this, right? That would be, let me draw a line so you know it's unloading. That would be inelastic. Okay? So those are kind of the three classes. We'll talk a little bit more about viscoelastic when we get to that point. Because viscoelastic kind of is a blend between these. So viscoelastic material will go back to its original state, sort of like an elastic material, but it doesn't follow the same curve back. So it's, in that sense, it's like an inelastic material, and because it's time dependent, we call it anelastic. But that's just a little preview. We'll talk a little bit more about that later in the semester when we get to viscoelasticity. Okay, so right now we're going to focus primarily on elastic materials that are linear elastic. So let's just say that for a linear elastic material, we describe it with Hooke's law. So hopefully you remember from long ago in your early years as an undergraduate that in the 1D case, Hooke's law looked pretty simple. It just said that stress, sigma, is linearly proportional to strain, epsilon, and it was the constant of proportionality was E, right, where we defined E as the Young's modulus. Okay, then hopefully you became a little bit more sophisticated in your understanding of mechanics, and you moved to something that would be in 3D, and you said, well, we know that stress is really a tensor, it's not really a scalar quantity, and so you would write the stress tensor as actually a stress vector, and you'd say that that stress vector sigma is equal to this matrix, the stiffness matrix C, times a strain vector epsilon. Okay? Hopefully what you remember is that this matrix C is a 6x6 symmetric stiffness matrix. Okay? I deliberately don't say tensor because that 6x6 matrix is actually not a tensor. And we can define also these quantities, these stress vectors, where, so let's say sigma, if you remember, that looks something like sigma 1, 1. It was the 6 unique stress components, sigma 2, 2, sigma 3, 3, typically organized by the normal stresses followed by the shears. The shears can sometimes take different orders, just simply depending on a convention that a particular book or something uses. And then the strain vector, was related to the strain tensor, but it also wasn't a tensor either. We had our normal strains, epsilon 1, 1, 2, 2, and 3, 3. And then we actually had engineering strains for our shear strain, so that would be 2 epsilon 1, 2, or you wrote it as gamma 1, 2, 2 epsilon 1, 3, and 2 epsilon 2, 3. Okay. Now, that's not sort of the language that we use so far in this class. We've spoken really heavily in terms of tensors. So we want to be able to retain our sort of tensor language to talk about the constitutive law. And so I want to introduce what that law looks like in its sort of full tensor form. So in the general case of a linear elastic material, so linear elasticity, we can just simply relate sigma ij to some epsilon kl with this quantity c I j k l. Okay, that's the general form.Cijkl is a fourth order tensor that's going to be symmetric, although it's hard, I understand, to visualize symmetry in 4 dimensions, but it's symmetric in ij, in kl, and swapping ij and kl. Okay? Not going to talk too much more about that, but the idea is that if we look at that, that gives us 21 independent elastic constants. Hopefully you recognize if we talked about a 6x6 6x6 matrix that represented the stiffness that we talked about previously and that you learned about previously probably, then that symmetric stiffness matrix also has 21 unique constants. So it's the same number of unique constants in the 6x6 matrix. But you probably also remember that when you had done most of your calculations, even in a 3D sense, you really only cared about 2 quantities, except unless you maybe have taken a composites course and looked at some anisotropic behavior. So in the case of an isotropic material, we actually only need 2 constants to describe the material behavior. And so typically you would have that be something like the Young's modulus and the Poisson's ratio, or the Young's modulus and the shear modulus, or the shear modulus and the Poisson's ratio. If you knew 2, you could always come up with that third elastic constant. And that's actually true here, even in the full tensor form. That's nothing that you wouldn't expect. I'm not going to show how we get to that state. I'm just going to give you the form sort of without proof, because it's just something that is important for you to know right now. But here we go. So in the case of isotropic materials, okay, we need 2 unique elastic constants. Let me remind you a little bit. What does isotropic mean? Well, isotropic means it's the same properties in all directions. Okay, so if you have a material that has those properties, which frequently in engineering we encounter these, we typically handle things like steel or aluminum or copper or titanium all as isotropic materials. So we need 2 constants. So for example, we would have maybe E and nu would be a set of constants, or maybe E and G, the shear modulus, would be a set of constants, or maybe G and nu. And there's actually more constants that we could use, and we're going to actually show you those here in just a second. But you maybe remember bulk modulus would be another example from maybe a fluids course. So here it is in tensor form. An isotropic material has a constitutive law that takes the form sigma ij is equal to lambda epsilon kk delta ij plus 2 mu epsilon ij. And let's call that equation star. Okay, that's Hooke's law for an isotropic material in 3 dimensions. And you're probably wondering, what's this lambda and mu? Please give me back E, G, and nu. I remember what those are. I'll show you here in just a minute, but lambda and mu are called what are called Lemay constants. Okay, and there's nothing special or tricky about them. They're just yet another set of constants that can be used to describe elastic behavior. We can show, and I will have you do so in a homework later on. So you can show that lambda and mu are related to our conventional constants via the following. So we can write the shear modulus G, this is the easiest one, that's just equal to mu. So mu is actually, even though it's called Lemay constant, it's just the shear modulus. The Young's modulus E is a little bit more complicated. It's related to some combinations of mu and lambda. It looks something like this. Mu times 3 lambda plus 2 mu divided by lambda plus mu. Okay, that's Young's modulus. And if you want the Poisson's ratio, is equal to lambda divided by 2 times lambda plus mu. That's the Poisson's ratio. So what does all that mean? That means that our constitutive law gives us another, so sigma ij, right? There's 6 unique components of that. So it gives us 6 additional equations. It doesn't introduce any new unknowns. We already had both sigma and epsilon being unknowns. So it introduces 6 new equations that now give us basically 15 equations to 15 unknowns to solve for in our linear elastic governing equations. So what do those look like? Adding the constitutive law, it completes the system of equations that governs linear elastic behavior. So we have, here's our set, sigma ij comma j plus rho bi is equal to rho ui double dot. And then we also have the strain displacement relations, epsilon ij is equal to 1/2 ui comma j plus uj comma I. And then finally now we have our constitutive law, which looks like sigma ij is equal to lambda epsilon kk delta ij plus 2 mu epsilon ij. So there's 6 equations here plus 3 equations there is 9 plus 6 more equations here is 15, and our unknowns, so there's 15 equations for 15 unknowns. Right, and those unknowns are sigma ij, epsilon ij, and ui. So we have a system of coupled partial differential equations that we have to solve for any understanding the response of any linear elastic material.